Okay. Um, okay. So after today's class, I'm going to how should I say? I'll prepare this survey form in Google Documents, and you guys need to fill out those forms to get a VPN account. So I'm going to prepare this Postgres database systems for you guys after this class. In order to access to the machine, you need to use a VPN. If you can connect to this internal network, then you don't need to use VPN. But if you are going to use Wi-Fi, campus Wi-Fi, or if you are in dormitory, I don't know, or outside the campus, then you need to use VPN to access our education cluster machines called the IMEAGE cluster. So as soon as the form and your accounts are ready, I will send out on. I will post an announcement explaining how you can use the cluster machines, etc. Anyway, so you need to use the cluster machine. You need to use the education cluster machines to submit your homeworks. So you don't have much time. I guess the first assignment will be handed out this Thursday. So you need to fill out the form by tomorrow, and so that you can start your homework from Thursday. So today I will introduce how to how to use relational models. So as we saw last time, this relational models data sets as a two-dimensional table as shown in this slide. So we have multiple rows and multiple columns, and each column represents an attribute of a specific entity. And those attributes are sometimes called columns, sometimes called attributes, or sometimes called fields. They can be exchangeably used, but most common terminology for this is attribute. And in each row we store independent object, independent entity. And in database systems, sometimes we call them rows or records or tuples. They can be also used interchangeably. And in each cell of the two-dimensional table, we can store a value, and every value should have a data type. But in database management systems, we use another terminology called domain. And domain is not just a data type, but it is more than data type. We call that additional feature as a constraint. Give me 1 second. Constraint. So suppose you created a database table where you can store exam scores. That exam score cannot be negative number, and it cannot be higher than 100. If you declare this data, if you declare the data type of this as an integer, then you cannot control the range of those values. But in DBMS, you can restrict what kinds of values can be stored in integer type attribute. We call those restrictions constraint. And if you have a well-designed database table, every value must be atomic. But if you look at this left example, in this first column, we stored the name and ID together. So this value can be decomposed into two different values. Then we say that this left database, attribute of this left table is not atomic. But on the right side, we have atomic attribute values in each cell. And in DBMS, you can store a special value called null in each cell. And the meaning of this null is different from the null values that you guys use for programming languages. So in programming languages, null often means 0, or it means usually 0 or false. But in DBMS, this null is not 0. This null means unknown value. And this null can be used for any kind of domain. Even if it is a string type, if it is integer type, any domains can have null values inside. Okay. So suppose that you modeled the real world and you identified a couple of attributes for a specific entity set. Then now you can define a relation schema using those attributes. So this R is how should I say? R is a relation schema, table schema for a specific entity set, and the definition of this R will be a set of attributes, and those attributes will be separated by commas. So an example is shown below. So suppose that you model the instructor entity set, and this instructor entity set has 4 attributes: ID, name, department name, and salary. They should be separated by commas, and they should be enclosed by parentheses. This is an example of relation schema definition. So relation schema is a template, and relation is actual instance that exists in disk storage or memory. So a relation can be considered as a set of records or a set of tuples or a set of rows. Row, tuple, record, they mean all the same thing. So this figure below is an example of a relation, not relation schema. Schema is just formal definition, and relation is actual table. And this relational algebra is based on set theory, the mathematical topic. So in set, we don't care about order of entities. We don't care about order of elements of the set. So similarly, in relational algebra, order of tuples do not mean anything. It can be stored in any arbitrary order. So if you look at this example, relation instance, these records, these rows are not sorted by any attribute. If you look at ID, they are not sorted. If you look at name, again, they are not sorted. So ordering doesn't matter in relational algebra. Okay, so now we know what is relations. And database is a set of it is a set of relations. So suppose that you model the instructor relation, and student relation, advisor relation, and so on. And a set of these relations forms a database. If you have any question during my lecture, you guys are free to raise your hand. Okay. And now let's talk about key. Key is an ID. Key is an attribute or multiple attributes that can uniquely identify a particular tuple in a table. So if you look at this example, what is the key? ID. If you look at these ID, there are no duplicate IDs. So using an ID, we can uniquely identify a particular record. Similarly, if you look at name, we don't find any duplicate. So it seems like name can be also used for, name can be used as a key for this table, right? But in real world, there can be some people who have the same names. So name can be used as a key, but it is not recommended. Next, let's formally define the notion of keys. So what is R? R is a relation schema, which is a set of attributes. And K, the key K is a subset of relation schema. So this means that K is a subset of the attributes defined for relation R. So let's suppose R contains ID, name, department name, salary, and so on. And this K can be ID and name, or just ID, or it can be a set of attributes that can uniquely identify each tuple stored in this relation R. Okay, that's the definition of a key. And you need to distinguish three different types of keys. The first one is super key. A super key is a key that is sufficient to identify a unique tuple in relation R. This means that if ID alone can uniquely identify a particular record, even if you have some additional attributes like a name and department name, still you can uniquely identify a particular record using those set of attributes. Okay? So it is a superset of a key. That's the meaning of a super key. But do we really need this name? No. This is not necessary to uniquely identify a key, right? So let's eliminate this name. Then that key becomes a candidate key. So candidate key is a minimal super key. Okay, so in that instructor table example, ID is a candidate key. And there can be multiple candidate keys. So if you look, if you remember the previous instructor table instance, names can be also used as a key because there are no duplicate names in the table, right? So suppose we have ID as a candidate key and name as another candidate key. Then as a developer, you must choose one of those two candidate keys. So suppose that you selected ID to be used as a key for the table, then we call that ID the primary key. So primary key is a selected candidate key by a developer. Is this clear? Clear? Can I move on? Okay, good. Oh, purpose of slide. Okay, so DBMS query language is based on this set theory. And what kind of operators are you aware of in set theory? What kind of operations can you do with two different input sets? Union, intersection, and set difference, right? In addition to those three set operators, this relational algebra defines some additional operators. For example, filter operation can be used. So we may want to select just a couple of elements that satisfy a given select condition. That kind of operators are defined in this relational algebra. So relational algebra is just an extension of set operations. And similarly, there's another mathematical theory called relational calculus. And this relational calculus is more like mathematical, it uses more mathematical notions like this bottom example. So you can define a query as a set of tuples such that the tuple belongs to student relations, and SSN attribute of the tuple must be 1 to 3. So you can define a given query using these set notations, and we call this kind of language relational calculus. But expression power of relational calculus is no different from relational algebra. And since relational algebra is much more intuitive, and it is usually the query, the length of query is much shorter than this relational calculus, people prefer to use relational algebra to relational calculus. So in this lecture, we are going to completely ignore this relational calculus and focus on relational algebra. Okay? But transforming this relational algebra into relational calculus is very trivial. So even if you do not learn relational calculus, I believe that it's not going to be any problem. So in set theory, we know union, intersection, set difference. And in addition to those operators, this relational algebra introduces some more operators. But so we have a bunch of relational operators. But among those many relational operators, these 5 operators are considered the most fundamental: union, selection, projection, Cartesian product, and set difference. The reason is all other relational operators can be defined as a combination of these 5 operators. So we consider these 5 operators are the most fundamental relational operators. So let's look at each of the operators. So union, everyone knows what is union. In DBMS, to apply this union operator, we need 2 sets. So union is a binary operator. We need a left operand and right operand, and this left and right set must have the same number of attributes and same domain types. So if you look at these 2 examples, we have 2 columns, and left column of this left table is A, and also on the right side we have the same attribute A. So we can apply this union operator. Set difference is no different. Set difference is also binary operator, and we need the same number of attributes, and their domains must be the same. And as everyone knows here, if you apply this set difference, then common tuple will be removed in the output relation. Next operator, this is new to most of you guys, I believe, selection operator. And we use this Greek symbol, small sigma, to indicate the selection operation. So basically this is a filter operator. Suppose we got this table ABCD that contains 4 tuples, and we want to select records that satisfy this given predicate. This predicate says that value of A must be equal to value of B, and D must be greater than 5. So let's look at this example table. A is alpha, B is alpha. Okay, this satisfies the first condition. But D is also greater than 5. So this first tuple satisfies this given predicate. Therefore, this first tuple must be included in the output table. But the second row doesn't satisfy this first equal condition. So this is not going to be included in the output table, and so on. So the first and last one satisfies this given predicate condition, and the output, therefore the output table contains only 2 tuples. Okay, this is called the selection operator. And in algebra, we put that predicate as subscript of this small sigma symbol. Okay, and this is a unary operator. It doesn't need two sets. It needs only 1 set. So that 1 set should be included inside the parentheses here. Okay, this is the notion of. This is how we write selection operator in the algebra. So let's look at another example of selection operator. Suppose you want to submit a query to find computer science major student named Kim. How can you write this query in relational algebra? We have student table. This is the only table we need. And here we have filter condition, name and major. So put sigma symbol, and name must be equal to Kim, and department name must be equal to comp sci. Okay, this is how we write a selection operator for this given query. Next operator is called the projection. And for projection operator, we use capital pi symbol. And again, this pi, projection operator is a unary operator. So it needs only one relation as an argument. And this projection operator requires any number of attributes as a subscript. And those attributes must be separated by commas as shown in this bottom example. So what it does is it eliminates attributes that are not listed as a subscript. So here we currently have 3 attributes, but if you look at this algebra, it has only A and C. That means attribute B should be eliminated in the output relation. Okay? And after eliminating this attribute B, now you have duplicate. Previously, because of B, we had this first and this first row and second row were considered different. But after eliminating attribute B, the first row and second row became the same. So we need to eliminate this duplicate. Okay, that is projection operator. Easy. Another example, suppose we want to find ID of computer science major student. We have a filter condition and projection condition. ID, we want to retrieve only ID. This is a projection operator. And we want to filter out non-computer science major student. This is a filter condition. So we need to combine select operation and projection operation. How can you write this query in relational algebra? Let's apply filter operator first. So department name is the only filter condition here. And it is a unary operator that requires a student table, student relation. After that, we apply projection operator to retrieve only ID. Okay. Oh, by the way, so in my lecture slide, we have parentheses to include this sigma operator, but it is optional. You can eliminate it when it is obvious. You don't need to have these parentheses. Next operator is called Cartesian product operator, and we use this cross symbol to denote this Cartesian product operator. It is because it works similar to multiplication. And this Cartesian product operator is a binary operator, so we need two operands R and S here, and suppose we have these two input relations. And this Cartesian product operator allows us to have any arbitrary number of attributes on the left side and right side. The number of attributes don't have to match, and their domains don't need to match any two sets can be used as operands for this Cartesian product operator. So if you apply this Cartesian product operator to these two input relations, what's going to happen is the output table will have 5 attributes. The number of attributes of R is 2, number of attributes of S is 3. So if you just add these two numbers and prepare the output table. So output table will have all the attributes of the input tables. And then to produce this output table, it works as if we run nested loops in programming languages. So we iterate every tuple of the left relation in the outer for loop, and then we iterate every tuple of the right relation in this inner for loop. So for every row I in relation R, we iterate again for each row J in S, and then concatenate those two records and put it in the output table. So you match alpha 1 with alpha 10A and put it in the output table by concatenating those two tuples. And then you match alpha 1 with beta 10A and put it in the output table. You keep doing this until you meet the end of the last record of this right relation. And then move on to the next record of this left relation and do the same again and again. So when the number of tuples of relation R is n, and when the number of tuples of right relation is m, the output table of this Cartesian product will have n times m tuples. Okay? We just generate all possible combinations of these two tables. That's Cartesian product operation. And another example is given here. Suppose we want to find name of students who take course SW 3003. How can you write this query? Name of students are stored in student table, and course information, who take which course, this course taking information is stored in another table, take. So in take table we have student ID and course ID and what letter grade each student got in each course. Those information are stored in take table. Let's assume that. And student table has student ID, name, and department name. So information that we need are scattered across these two tables. We need a name, and we need this course taking information from another table called take. So we need to combine somehow these two tables. In that case, we use this Cartesian product operation. Okay. So first, just apply Cartesian product. Let's assume we had only 2 tuples in student and 3 tuples in take table. Then the output of this Cartesian product will generate total 6 tuples. Kim Computer Science and 3 records are stored for this Kim Computer Science. And for the second student, we generate another 3 output tuples. Okay, so that's the output of Cartesian product. This is not what we want. We want to find name of students who take a course SW 3003. Do we need this second tuple? No. Why? Because this course taking information is for student with ID 20. We need to eliminate this tuple from this output table. How can you do that? We should apply select operator. Select operator and compare this first ID with the second ID. And we need to select tuples that have matching IDs. If they do not match, we need to eliminate it. We need to filter out those unmatching records. So to eliminate these unmatching records, we put this sigma symbol with predicate. Currently, we have two attributes with the same names. This is confusing. To avoid this confusion, in relational algebra, we are allowed to use dot operator. So student.id means the ID column from student, and take.id means ID column from take table. By having this path expression, we can avoid such confusion. Okay, after selecting those matching records, what should we do? We need to apply projection operator to find only the name. Oops. Oh, that's not it. Give me a second. Sorry. After finding out those matching records, we should consider another predicate. So we want to find the names of the students who take course SW3003. So we have another filter condition. So the filter condition should come after this logical AND operator. After that, we should apply projection operator to find the name. Okay, are you guys following? Any question?
I think it's to be to condition product in entire data. So I think first of all, in take creation, first selection and product. I think is the better.
Yeah.
Is being granted.
Great. Yeah, that's actually a really good question. So this Cartesian product is very expensive. Cartesian product is really expensive. So sometimes we can apply this filter before we apply Cartesian product to shrink the size of the input table. We call that query optimization, and there are many interesting query optimization techniques, and we will cover after the midterm exam, probably. Yeah. Good. No. I think we are going to talk about some level of optimization techniques before the midterm exam. So, the same given query can be represented in a diverse way. This query can be written in this expression, and we can reorder these operators somehow to get the same output table. So there can be many different ways of writing a given query in relational algebra. And some relational algebra expressions will perform better, some expressions will perform poor. And it is the responsibility of DBMS to find the most efficient query execution plan. So DBMS will rearrange these operators, and after rearranging these operators, it estimates the cost of executing those operators, and then it chooses a better plan to find the optimal query execution plan. There's a chapter to discuss this issue. But for now, as an introduction class, let's forget about those optimization, and yeah, I'm just trying to explain how this Cartesian product works and why this Cartesian product is needed. So this Cartesian product is needed when we have information scattered across multiple tables. Okay? So this Cartesian product combines those scattered information and generate a single table. Okay? Clear? Good.
Professor, it seems like that only union and set difference operators have to have some good same attributes.
Yeah. So Cartesian product doesn't require us to have the same number of attributes and same domain. We don't need it. Selection operator is unary operator. It needs only one relation, so we don't care about those number of attributes. Projection also is unary operator, so we don't care about that. And what else? Let's go back here. So this is binary, this is unary, binary, binary. Union and set difference and intersection, it is not fundamental operator, so it is not listed here, but we have intersection operator. Oops. Intersection is also binary and requires the same number of attributes and domain. Not this one. Set difference, union, they require the same number of attributes and domains. Cartesian product doesn't require that. And I will introduce a couple more relational algebra operators, and I'm going to explain when we need this condition. Let's move on. Oh. So these 5 operators are considered fundamental, and we have some more operators like set, intersection, join, rename, division, group by. So let me introduce each of these operators one by one. Give me 1 second. Where is set difference? I haven't introduced how set difference works. I guess it is somewhere in later slide. I think the ordering issue. We have ordering issue here. I will fix that next semester. So we have intersection operator. Again, we need the same number of attributes and same domains, and we only find common tuples and put those common tuples in the output table. Easy. So question here is why set intersection is not a fundamental operator. It is because this set intersection can be written using set difference operator. So set difference is a fundamental operator, and this intersection can be rewritten as follows. So consider we have 2 sets, CS major and electrical engineering major. This is the set difference. This is intersection. How can you find this intersection without using intersection operator? First, you deduct electrical engineering major from computer science major. Then you will get these tuples, right? After that, you do the same. Oops. After that, you do the same, but this time you deduct these tuples from computer science major. So if you deduct this amount from computer science major, you will get the intersection, right? So that is why this intersection operator is not categorized. It is not classified as a fundamental operator. Okay. Next, natural join operator. Natural join operator is denoted as this ribbon symbol. And basically, this natural join operator is a combination of Cartesian product and select operator. And we need this projection operator as well, but let's talk about this projection after I introduce how this natural join works. So natural join is a binary operator. We need left and right relations. And for each pair of tuples from R and S, we check whether their common attributes have the same values. If their common attribute values are the same, then we put that, we combine those two tuples and put it into the output table. I guess it'll be easier to explain this using an example. So consider we have a student table and take table. And let's look at attribute ID. This is the common attribute. Other than ID, we don't have any other common attribute. Okay? And when you apply natural join, we only look at common attribute, ID, and we iterate that nested for loop and find out only matching records using the common attribute. So for the first tuple of student table, we scan takes table and then find out common value in that common attribute. Since 10 and 10 matches, we concatenate this first tuple with the first tuple of take and put it into this output table. Okay? And this is the only matching record in takes table. Then we move on to the second tuple of student table and then scan takes table again and find the matching record and combine these two tuples and put it into output table. Okay, we do the same for the last record. Okay, so basically this natural join operator is Cartesian product and select operator. And the filter condition of this select operator is to compare the values of common attributes. Okay? And there's one more difference with the Cartesian product. When you use Cartesian product, when the left table has n attributes and right table has m attributes, then the total number of attributes of the output table will be n plus m. But when you apply this natural join operator, we will keep only one single common attribute. So on left side, left table has ID and right table also has ID. And we are going to put those tuples that only have the matching values of the ID. There is no reason to have two duplicate ID columns in the output table. Therefore, the output table of natural join will retain only one single attribute. Okay? So when this left table has n attributes and right table has m attributes, and if the number of common attributes is k, the output table will have n plus m minus k attributes. Right? Is it clear? Clear? Question? K is the number of common attributes. So in this particular example, we have only one single common attribute in either side, in both sides. So K will become number 1. Therefore, we eliminated one column in this output table so that we don't have two duplicate ID columns. Yeah. So we have currently 3 attributes and 3 attributes. If you look at this bottom table, we have 5 attributes. It is because 3 plus 3 minus the number of common attributes is 1. Okay. That is, let's go back to the previous slide. That is why we have this projection operator. The objective of this projection operator is to eliminate redundant column in the output table.
What happens if there, for example, some tuples have same with ID, but some tuples same in name? Then what happens if they're natural join? So, for example,
10 ID and what?
Who has
Lee as a
yeah.
mhm.
And second and third case is
Mhm.
10 ID and relay.
Mm.
Then
Okay,
what
okay.
happened in-
Okay, I guess your question is so 10, 23, this is student, and Kim, Lee, and Park. And let's say we have take table, and in take table, ten SWE 3003, SWE 4004, and so on. Is this your question? And 20, I don't know, 101, 201, 30, 33. Then how many output, how many tuples are we going to have in the output table? So this natural join will find matching record using the common attribute. So for this first tuple of student, we found two matching records. So the output table will have two records for these two relations. So 10 Kim SWE 3003 will be put in the first row. In the second row, 10 Kim SWE 4004 will be inserted. And for Lee, again, we will have two more records. And for Park, we are going to have three more rows. So total, seven records will be inserted in the output table. Okay? Good. Okay, let's move on. So, this query requires some information stored in student table and some information stored in the text table. So we apply the natural join. After that, we have this filter condition. We only care about courses, course with ID SW3003. So we have a selector condition here and projection operation. Oh, did we just look at this query in previous slide? Yes, we saw it. So let's compare those two expressions. This is it. So we have a Cartesian product and select operator and how should I say predicate with AND condition. That relation algebra expression does exactly the same job with this given expression. But this one looks simpler, it is shorter and more intuitive. So people prefer to use this natural operator, natural join operator, compared to that Cartesian product. So this natural join operator will generate these three records, and then this filter condition, select operator will eliminate these two records from this table, and then this projection will eliminate unnecessary attributes from the output table. So Lee will be returned. A single scalar value will be returned from this query. Okay. This natural join operator can be used for those tables with multiple common attributes. So in this example, left table has A, B, C, D, and right table has B, D. So common attributes are B and D. And when you perform natural join operator, then 4 plus 3 equals 7, but we have 2 common attributes, so 5 attributes will be stored in the output table. And let's do that nested loop check. So for the first tuple, we scan this right table and find out whether B, D's values are 1 and A. Here we have a matching record, and we have another matching record. So we join these two tuples and put it in the output table. Okay? Can I move on? Can I move on? Okay. Oh, I have an animation. This, they match it. So we put it in the output table, and these two also match it. We put it in the output table, and we move on to the next row of the left outer for loop. And then, oh, don't we have any 2A? No, we don't have 2A on the right side. So we move on to the next 4B. Do we have a 4B on the right? No, you don't. So we move on to the next one, 1A. Again, this one and this one match it. So we put those two combinations into the output table. And do we have a 2B? Oh yes, we have one. So they, those two tuples were combined and put it in the output table. Next operator is called rename operator, and we use this row Greek symbol row as the operator, and this is unary operator. And what it does is it simply renames table or attribute. Table can be renamed, also attributes can be renamed. So before, suppose table T existed, and somehow you want to change the name of the table T if you want to change T to S, you write it like row subscript S with T inside the parentheses. Why do we want to do this? The answer is sometimes the same table is used multiple times in a single query expression, and that may confuse people. So to avoid confusion, sometimes it is recommended to change the name of the table. I don't think I can give you a good example at the moment. When you learn more advanced queries, I will explain why this is necessary again. Oh, we have a use case here. This is simple use case. Okay. So suppose we have this table. This table contains parent-child relationship. So Mary is parent of Tom. Mary is a mother of Tom. And Peter is a father of Mary. And John is a father of Tom. So this hierarchy, genealogy, can be written, represented as this kind of reverse tree structure. And the given query is to find the grandparent of Tom. How can you do this? How can you write this query? You need to use this Cartesian product for the same table. Let's name this table as a PC. So you should apply Cartesian product for the same PC tables. So if you do that, then this Cartesian product will give you total 9 records. So Mary Tom will be put in the put it in the first row. Mary Tom Peter Mary will be put in the second row, and so on. And your job is to find out tuples that have the same name in the child column of this left PC table and parent column of the right PC table. Okay, so without this rename operator, the query will look like select child equal parent PC Cartesian product PC. Then we will be confused. What is this child? Is this child refers to the child column of left PC or right PC? Even if you put the table name using this path expression, still you will be confused. Is this left PC or right PC? So to avoid this kind of confusion, sometimes we need to use this rename operator. After renaming, you can specify that this child is for the left PC and this parent is for the right PC. Okay. Next operator, division. Personally, I think this division is the most difficult relational algebra operator. And this division operator is useful for expressing queries like this. If a query statement has every condition or all condition, you should think of division operator. Why? This division operator works exactly the opposite of Cartesian product. So suppose you have a relation R that contains two attributes, x and y, and another relation S has an attribute y, which is subset of this left relation R. Then if you divide R by x, S, then the output table will contain x attributes that match all y values stored in table S. I don't think most of you, it's difficult. But if you look at an example, I guess you guys are going to get some intuition better. So let's look at this example. We have a text table. This text table has who took which courses. So student with ID 10 took these two courses. Student with ID 20 took these two courses. Three courses. And student with ID 30 took these two courses. And the course table has these three records. And we only care about computer science courses. So let's first eliminate electrical engineering course by running select operator. Okay. So by running select operator, we eliminated this last tuple. And by running projection operator, we eliminated the department name. So now we got SW 3003 and SW 4021. Okay, now we will divide this text table, take table with this output table, as shown below. Then what will be returned? Let's check whether student with ID 10 took these two courses. He took SW 3003, but he didn't take SW 4021. So student 10 doesn't match. So student 10 will not be inserted into this output table. But if you look at student 20, he took these two courses and additional courses. So this student 20 satisfies this division condition, and he will be put into this output table. Again, similarly, student 30 took these two courses, so he will be put into this output table. Okay, now let's go back to the definition and think about this definition. Suppose we have a table R with two attributes X and Y, and table S has attribute Y. And if you divide R by S, you check whether any given X contains all values stored in S. Okay, now it makes sense. Okay, why is this the opposite of a multiplier? Let's multiply. Let's perform Cartesian product with this table and this table. Then what we get is 20 SWE 3003, 20 SWE 4021, and 30 SWE 3003, 30 SWE 4021. And these four records exist in the given left relation. Right? We missed a couple of records, but the output of this Cartesian product is guaranteed to be subset of the original table. That is why it is the opposite of multiplier. Then you may wonder why. What about those missing records? You know, even if in multiplication and division, sometimes we have a remainder, and this division operator sometimes delete those remaining numbers, right? Same here. If this record doesn't match, then they will be eliminated in the division operator. So you may consider this as, and this one as, remainder of division operation. Is it clear? I see some students are nodding your heads, but most of you guys look confused, especially those guys sit on the back or on the side. Question?
In the division operation, so S field must have one or?
No, the divisor can have arbitrary number of attributes as long as those are the subset of the what is it? Dividend? No, the left operand. I learned mathematics in Korea, so what is this? So, A divided by B. We call this divisor, right? Dividend, right? Oh, okay, I was correct. I wasn't sure about it. Okay, so in this relational algebra, this division operator also requires that divisor is a subset. I mean, attributes of divisor must be a subset of dividend set. Okay. So another example. Suppose we have a table R that has a student ID and the project numbers that students are working for. And we have another table that contains only project numbers. So if this is divisor, then what will be the output? The answers are already given below. So you need to check which ID is associated with project P2. So 10 P2, okay, let's put 10 in the output. P2 is also here, so 20 will be inserted into the output. P2 is again here, so 30 will be inserted. 40 is also associated with P2, so 40 will be inserted. This is the output of this operation. And if S2 has these two tuples, then what will be the output of this division? You should check whether 10 is associated with P2 and P4. Okay, so 10 is stored. For ID 20, we have P2, but P4 is missing, so 20 cannot be inserted. Again, ID 30 doesn't have P4, so it cannot be inserted. 40 has P2 and P4, so 40 can be inserted into this table. I guess we can do the same for the last example. So, division is reverse of Cartesian product. And division is not one of those 5 fundamental operators, mainly because this division operator can be rewritten as follows, that uses only 5 fundamental operators. I'm not going to explain. This is in the math class.
Will that be an exam?
Huh?
Will that be an exam?
No. Anything that I skip, you can completely ignore it in the exam. Yeah. I also hate mathematics, so. Good question. Okay, I guess we are almost done, right? Group by and okay, group by is the last operator for today. So suppose we have this table, instructor table. Sometimes you may want to calculate the average salary of the instructors after classifying these instructors into their department. So I want to know how much computer science instructors make and how much electrical engineering instructors make. So suppose those kind of queries, then we use this group by operator. This group by operator uses this alphabet G as a symbol, and it has a left subscript and right subscript. And the left subscript is classification, what kind of attributes we use to classify each group. And the right operator is aggregate function. Aggregate function like average, maximum, minimum, and count, which counts just number of tuples, and then we have a couple more. So this given group by query classifies this table based on the department name. Currently, these tuples are not sorted, but to group these records based on the department name, we need to sort them. So we just sorted, and we will perform projection operation as well. Any attribute that is not listed in the right subscript will be right subscript and left subscript will be eliminated. So if you look at this given query, ID is not used, name is not used, so we completely ignore these 2 columns. And for the remaining attributes, we perform sorting. So physics are grouped together, finances are grouped together, history, computer science, we have only 1 electrical engineering, and so on. So after grouping these records that have the same department names, we perform this aggregate function. If it is an average, we calculate the average of these 2 numbers, average of these 2, average of these 2 and 3, and so on. And then generate the output table. For each group, we have just 1 single record. This is the output of aggregate function. So we had 2 records, but they are going to be grouped and stored as a single tuple in the output table. This is a group by operator. Okay? Mm. Mm.
So the authority is something free?
Sorry?
The authority is something free? Because
Is it incorrect? Oh, yeah. Sorry, I just blindly copy and pasted. I didn't do the. Yeah, I told you I hate mathematics. Yeah, it shouldn't be 95,000. It should be the average of digital number. Maybe if I change this to max, will that make it correct? Yeah, okay. No? You do the math. I don't want to do it here. Okay, so so on the right subscript, on the right side of this group by operator G, we have we need aggregate function like minimum, average, max, and so on. On the left side, we need to have a couple of attributes that should be used to define a group, define independent group. And usually we have just one attribute, but sometimes you may have multiple attributes separated by comma. And even it is possible to have no attribute at all. If you don't have any attribute on the left side, then it performs this aggregate function for all records. So it is going to return just a single scalar number. Okay. So this G count ID instructor will just count how many IDs exist in the current instructor table without any group. Okay. And formal definition of this group by is written here. You guys read it. And we have about 2 more minutes left. And I don't think we have time to cover these practice questions. So suppose that you got these relation schema and try to translate this given human query into relational algebra expressions. And in the midterm exam, this kind of questions will be asked. So this will be a good practice for you. And let's solve these queries on Thursday together. Yeah. Okay, good. I'll see you Thursday.